This is part one of differential equation application, and most of what we'll be doing as far as applications is based off of this expression. So the rate of change of y is proportional to y. So what this means, the rate of change just means a derivative. So rate of change is how something is changing, is basically a derivative of something. And so the derivative of y is proportional to y. So how something is changing, the derivative of something is proportional to itself. So the way we can write this as a differential equation is the derivative of y, and all these deal with how something is changing with respect to time. So we're going to say with respect to t, so dt. So the rate of change of y, so dy dt, is proportional. So we're going to put k times y. So the proportionality is where I got the k from. So k is going to be the proportionality constant. And you can think of it as if it's doubling every hour, or if it's tripling every couple of hours, or something like that. So how something is changing has to be some constant, some proportionality constant. So this is the differential equation that describes this statement. And the way we can solve this. So if I try to find the solution to this, I do a separation of variables. So I'm going to go ahead and divide over the y, so dy over y. I'm going to leave this k, this constant, over here on the right side, and it's going to be a k times dt. And I go ahead and integrate both sides. The integral over here on the left, this is the same thing as the integral of y to the negative 1. So it's going to be ln absolute value of y. And then this integral of k, which is a constant, with respect to t, is going to be a k t plus c. I go ahead and take e to both sides. This undoes the ln, so it's absolute value of y. And then I apply the down constant rule. So e, the c drops down in front, e to the k t. Well, there's a down constant rule. And so this is all going to be an applications-based problem. C is going to be the initial amount, and you can't have really a negative initial amount for most of these problems. So we're going to go ahead and just drop the absolute value. We don't have to worry about it being negative, and we'll just say c e to the kt. That's going to be our solution. So the significance of this is that the solution to this differential equation is this. It's exponential. You might recognize this as exponential growth or exponential decay. So this differential equation has this as the solution. And you might have seen this before in pre-calculus and definitely in algebra 2. We talk about compound interest. You might have seen this formula where A is the amount, R is the rate, sort of like the decimal they give you, or the percentage, or maybe you saw this in this way where A is the amount, and then K is, if it's positive, it's exponential growth. If it's K is negative, it's exponential decay. So this is something that you guys have seen and worked with before, but maybe you don't really know where they got the equation from. And the significance of it is the equation comes from this statement, and this is the solution. Here's the important part, is that whenever we're given a differential equation like this, it's going to have this form of a solution. So c is going to be a constant, and then k is called a different constant, the constant of proportionality. So this k determines if it's growth or if it's decay. Alright, let's go ahead and copy this into your notes if you haven't already, and let's go over an example. So example 1, you can go ahead and pause it and copy down. example 1 says the rate of change of y is proportional to y, so I can write my differential equation. And the nice thing about having already solved this is I can just jump right to the solution, being y equal to c e to the kt. And then I can just go ahead and use the information they give me, the given conditions is that when t is equal to 0, y is equal to 2. And they also give me another condition that when t is equal to 2, y is equal to 5. And so I go ahead and apply my conditions to figure out what one of these constants is. So I'm going to apply the conditions, and I'm going to go ahead and plug in 0 and 2. So it's going to be a 2 is equal to a c e to the k, and the t is going to be 0. So basically 2 is equal to c e to the 0, and anything to the 0 power is equal to 1. So basically 2 is equal to c. The next thing I want to do is apply the other condition. So I'm going to apply another condition that t is equal to 2 and y is equal to 5. So I can say t Alright, so I know my c value is 2, so I can say 5 is equal to 2 e to the, so I don't know what k is, but I know that the t value is going to equal 2. So I go ahead and basically isolate e to the k. So I go ahead and divide this over, so 5 over 2 is equal to e to the 2k. From here I go ahead and take ln of both sides, so it's going to be ln of 5 over 2 ln of e to the 2k. I go ahead and cancel off the ln and the e. So what I have is ln of 5 over 2 2k. I go ahead and divide both sides by 2. So my k value is going to be ln of 5 over 2 all divided by 2 is my k value. So I go ahead and punch this up on my calculator to figure out what this is. So give me 1 second for me to punch this up. So it's ln of 5 divided by 2 all being divided by 2 gives me a decimal of 0.458. Now I'm going to round to 3 decimal places, so my k value is equal to that. And then what I was asking for initially was to figure out the value of y when t is equal to 6. So my my solution is going to be y equal to 2 e to the 0.458 t. Now they want you to evaluate it at t is equal to 6. So I can just say y is equal to 2 e to the 0.458 times 6, and just punch this up on your graphing calculator. So just give me a moment to do that as well. So 2 e to that number times 6. And the answer I get is 31.25. In class tomorrow, I'll show everybody how I want them to deal with storing, or how to find this decimal. And there is a way that you can store the the exact value of it. You won't have to approximate it. So in class I'll show everybody how to deal with expressions like this and how to get answers like this. So, and that is it for this section.